Now that you know how to hook up your multimeter to measure current, let's build some circuits on our breadboard to better understand how current flows through a circuit. Reference the circuit diagram shown on the screen in order to build the series circuit with a 10 kilo ohm resistor and a 4.7 kilo ohm resistor. Utilize the resistor code to help you find those specific resistors. There are many different ways to build your circuit in series. As long as you go from positive to negative, one component connected right after the other, starting from positive through that resistor, connected to the next resistor to negative, that current has a path to take, your resistor series circuit will be good. I have my 4.7 kilo ohm resistor first next to my positive, and I have the 10 kilo ohm resistor connected to ground. I'm also using an extra jumper wire as a tester wire for my circuit. This will come in handy when we're measuring current. Notice I've reset my multimeter to have the red lead in the multi-jack. I try to not turn my multimeter on to measure current until I'm ready for it to start measuring. Let's start by measuring the current that leaves the power source before it enters the 4.7 kilo ohm resistor. In order to measure the current, we know that we have to put the multimeter in series with the components. The multimeter needs to be part of the circuit. So I'm going to open my circuit just like we did with the motor. We disconnected the alligator clip to the motor, opening the circuit so that we could insert the multimeter as part of the circuit. So I'm going to lift up my resistor that's connected to the 5 volts, and I'm going to plug in my tester wire into the breadboard where that resistor was plugged in. This allows me to open the circuit and still connect to the circuit components using my multimeter. You can see I have the 5 volts connected to this jumper wire. The circuit is open, so I'm going to measure current before it travels through that 4.7 kilo ohm resistor. I'm going to connect my red lead towards my positive and my black lead towards the negative. And now when I turn the multimeter on to measure current, current can flow through the jumper wire, through the red lead of the multimeter, through the black lead of the multimeter, to the first resistor, then the second resistor, and then ground. So we'll be measuring the current before it passes to that first resistor. I'm going to turn my multimeter to DC milliamps, and I am getting 0.34 milliamps. So let's reset our circuit, take out our tester wire, plug the resistor back into the 5 volt power supply, and then we want to measure the current after it has passed through this 4.7 kilo ohm resistor. So I'm going to pull that resistor out and replace it with my tester wire, opening that circuit so that I can connect my multimeter into the circuit. So current will pass through the 4.7 kilo ohm resistor starting from 5 volts through the 4.7 kilo ohm resistor, through the multimeter, then to ground. So we'll measure it after it's passed through that 4.7 kilo ohm resistor. Connect your multimeter leads and notice your current, 0.34 milliamps. Write this down along with the one that you measured leaving the power source. Let's repeat the process by resetting the circuit and measuring the current after it has passed through that 10 kilo ohm resistor. I'm going to pull it out of the ground, replace where that resistor was plugged in with my tester wire. Now that circuit is open and I can measure the current after it passes through that 10 kilo ohm resistor. Connect your multimeter and observe the current value, 0.34 milliamps. Are you able to recognize a pattern between the current as it flows through a series circuit? You should realize that the current is the same no matter what point you measure it in a series circuit. So the current can leave the power source, pass through each resistor, and go to ground, and it's not going to change value. Let's keep that on our minds as we shift to build a parallel circuit in order to understand how current passes through parallel circuits. Reference the circuit shown on your screen in order to build your parallel circuit on your breadboard. Remember, when building parallel circuits, the resistors are connected at a node at the top and another node at the bottom of the resistors. In order to build those in parallel on your breadboard, you'll put one end of the resistors in the same row, and you'll put the other end of the resistors in the same row. I'll use 2 jumper wires to connect these resistors to power and ground. Now that I have my circuit built, I can confirm that my circuit has 2 closed loops, starting from power through this resistor to ground and from power through the second resistor to ground. Now let's see how current behaves as it moves through this circuit. First, let's start by getting the current that leaves the power source. So we'll pull out the jumper wire from the 5-volt supply and use our tester wire to replace it, just like we did with the series circuit. This opens that circuit such that I can see current leaving the power source, opening, and it's open here, so I'm going to connect my multimeter. It'll be able to go through the multimeter once I have it connected, down through this wire, and then through the remainder of the circuit. Connect your multimeter and observe the value of current on your multimeter. I'm getting 1.56 milliamps. Now reset your circuit, take your tester wire out, plug your jumper wire back to positive, and now let's see what is the value of current that goes through the 4.7 kilo ohm resistor. I'm going to lift the 4.7 kilo ohm resistor up. I'm going to replace it with one of my jumper wires. Now I can see that this will be the current that passes through this 4.7 kilo ohm resistor once I connect my multimeter to the wire, the jumper wire, and the resistor. Connect your multimeter leads and observe the value of current. I'm getting 1.06 milliamps. That is different than the value of current leaving the power source. Reset your circuit and let's see what happens when we measure the current that goes through the 10 kilo ohm resistor. Do you have any ideas what might happen? Maybe make a prediction first before measuring to see if you're correct. Lift up the resistor and replace where it was plugged into with your tester wire. Connect your multimeter and observe the value of current passing through the 10 kilo ohm resistor. I'm getting 0.5 milliamps. Let's reset the circuit and let's measure one more place on our circuit. We have the current that's leaving the power source, the current through the 4.7 kilo ohm resistor, the current through the 10 kilo ohm resistor. Let's see what current comes back to ground. Lift up your jumper wire and replace where it was plugged into ground with your tester wire, and then connect your multimeter. The value of current that goes towards ground is 1.56 milliamps. That's the same as the current that left the power source. What do you also recognize by about the current that goes through each of the two resistors? You may realize that the current that goes through the two resistors adds up to be the current that leaves the power source or the current that comes back to ground. This is the foundational principle known as Kirchhoff's current law. With Kirchhoff's current law, we are seeing that the current that enters a junction point or node equals the sum of the currents leaving a node. You saw that here with the current that's entering this node here. So you know that the row is a node, and the current that enters this node here was 1.56 milliamps, and the current that left the node going this direction through this 4.7 kilo ohm resistor was 1.06 milliamps, and the current that left the node, this node here, through the 10 kilo ohm resistor was 0.5 milliamps. Now this is another node, the row 18 right here where the resistors are plugged into. The current entering this node here through the 4.7 kilo ohm resistor was 1.06 milliamps. The current entering this node here through the 10 kilo ohm resistor was 0.5 milliamps. And the current leaving the node through the jumper wire to ground was 1.56 milliamps. So you can see that the current entering this node added together to be the current leaving this node. Same thing here. The current that entered this node split between these two paths. Knowing that electrons are neither created nor destroyed, at a node, the current in must equal the current out. We can formalize this by saying the algebraic sum of the currents entering or leaving a node is 0. And this is what we call Kirchhoff's current law. Let's formalize Kirchhoff's current law by looking at the series and parallel circuit. If we're looking at the series circuit, we can identify the nodes by tracing where there are lines but no components. So we have node 1, node 2, and node 3. Knowing that Kirchhoff's current law is stating that the current in is equal to the current out of a node, and we can see that throughout the series circuit there's no separate path for current to take. the current in and out of the node has to be the same. And so for this circuit here, we have 0.34 milliamps that starts from the positive, travels towards the negative, and it stays the same as it passes through the 10 kilo ohm resistor and the 4.7 kilo ohm resistor. There's no separate path for current to split, so current is the same throughout the circuit. Looking at the parallel circuits, however, we can identify the node, and we can see that on the parallel circuit, there are only two nodes. But in addition to the two nodes, the current can have two paths to travel. We can have one path that goes through the 10 kilo ohm resistor. We can have another path that goes through the 4.7 kilo ohm resistor. We can see that the current in and out of the node has to equal one another. And we have 1.56 milliamps that goes into node 1, and coming out of node 1, passing through the 10 kilo ohm resistor is 0.5 milliamps, and coming out of node 1, passing through the 4.7 kilo ohm resistor is 1.06 milliamps. And you can see that 0.5 milliamps plus 1.6 milliamps equals 1.56 milliamps, which confirms Kirchhoff's current law that current in has to equal the current out. There are separate paths at the node for current to travel, causing it to split at that node. Additionally, I want to point out that the current is a lot smaller as it passes through a larger resistor, and current is a lot larger when it passes through a smaller resistor. Notice the 4.7 kilo ohm resistor has a current of 1.6 milliamps, where the 10 kilo ohm resistor has a current of 0.5 milliamps. If you've ever heard the saying, travel the path of least resistance, that also applies to current. Current will travel the path of least resistance, so it will send more of the current towards the smaller resistor because it's easier for current to pass through that resistor. You can think about that as water flowing through the different branches of a river. Whenever the branch has a narrow path, less water can pass through it. That's analogous to a large resistor. Whenever the branch has a larger path for water to pass through, that's analogous to a smaller resistor. More water can pass through. Let's formalize some implications of KVL. We know that if there are multiple paths for current to take at a node, it will split at that node. We know that the current into a node equals the current out of a node, and more current travels in the direction of lower resistance. So referencing the circuit shown, do you think I2 has a larger current value than I3, or does I3 have the larger current value? Knowing that the resistance that I3 passes through is a total of 1,500 ohms compared to the 1,000 ohms that I2 passes through, we can conclude that I2 will have a larger resistance value than I3. What is the current leaving the second node shown going towards ground? It should be the same as I1 because I2 and I3 add together as they enter that node, and the current shown traveling towards ground should be the same as I2 plus I3, which is equal to I1. When you have resistors in series, like the 500 and the 1000 ohm resistor on the right side of that circuit, you know that current will remain the same through those series resistors. Additionally, in order to find the total current leaving the power source, you have to calculate that REQ because all of those resistors play a factor into what that current value is leaving the power source. And then you can use REQ along with Ohm's law, knowing the voltage value, to find the total current leaving the power source. And then you can use KVL to determine the current that travels through each of the individual resistors within the circuit. Knowing how voltage behaves over a circuit, especially in series versus parallel, can help you understand the voltage at individual resistors, and knowing Kirchhoff's current law and how current behaves through resistors in series and parallel will help you understand both the current at a resistor and the voltage at a resistor, and you will be able to solve all the different pieces of information about specific components of a circuit. What happens if the component enters and leaves the circuit through the same node? Like the circuit diagram shows, the 4.7 kilo ohm resistor is connected to the same node on both sides of that resistor. Notice how the 4.7 kilo ohm resistor is now connected on both sides in the same node. Current is not going to pass through that resistor because, as we just learned, current travels the path of least resistance. This entire node is connected right here, and so current will never go through this resistor when it can go straight through the node to this resistor and then to ground. Current knows that it needs to go from positive to negative, so it's going to take the path of least resistance. Whenever there's any resistance in multiple paths, it will split and go towards each resistor. However, when there's no resistance, current is going to pass straight through and go to this resistor and then to ground. So this resistor is as if it's not even in the circuit. An interesting fact about Gustav Kirchhoff is that he was only 21 years old when he formalized Kirchhoff's voltage law and Kirchhoff's current law. At 21 years old, he was a student while developing these laws. Many of you are not even 21 years old. Imagine the possibilities that you all can do. If Kirchhoff can do it at 21, so can you.